at isomerism. We're going to cover the stuff that you need for Module 1. We're also going to cover the stuff that you need for Module 2. Okay? We're going to give a couple of hints about the stuff that you're going to need in Module 4, but we're not going to go to that in much detail. Okay? Right. So, we should know by now the functional groups in organic chemistry. What this session is going to be specifically around is going to include alkenes. Okay, but in terms of branch chains and so on, you should be able to name that sort of molecule. You should know what affects the boiling point of organic molecules, namely the strength of the intermolecular forces. Here is a table that shows all the different types of isomerism that you get. Very simply, you get two types of isomerism generally: structural isomerism and stereo isomerism. Okay. So, same molecular formula, but different structural formulae. Okay? So, same atoms, different arrangements in space. Whereas this one, okay, same molecular formula, but atoms occupy different positions in space. With stereoisomerism, you've got the same functional groups, okay, but just a slightly different orientation in space. Whereas structural formula, you've got different structural formulae as well, and we're going to look at that in a minute. So, to begin with, chain isomerism. This is where you've got the same functional groups, okay, but you've then got a branch chain or a straight chain, or two different branch chains, something like that. It's where the molecules are the same, the functional groups are the same, the position of the functional group is the same, but you've got a different arrangement of the chain. Are you happy with that? Chain isomerism. You've then got position isomerism, where you've got the same backbone, the same molecule, but your functional group is in a different place. So this one here will be 1-chlorobutane, and that's 2-chlorobutane, and they are different isomers of each other. Okay? So far, we've got all the same atoms, but different chain structure. Here we've got all the same atoms, okay, but different position of the functional group. So you can have propan 1-ol, propan 2-ol, and so on. Then you get functional group isomerism. And this is where you have all the same atoms, but they're arranged differently so that you've got different groups. So this is an alcohol with an OH, and this is an ether with an oxygen in the middle. Same atoms, different functional groups. Okay? And these three you should be familiar with at the moment. Okay? This is basically your Module 1 stuff. Chain, position, functional group. Okay? Different chain, different position of the functional group, different functional group, but with the same atoms. Another example of functional group isomerism is the difference between a carboxylic acid and an ester. Okay? Carboxylic acids and esters both have 2 oxygen atoms, okay? And they can have the same molecular formula. Which brings us on to stereoisomerism. If we look at both these two molecules here, these are both 1,2-dichloroethene. Okay? You've got the same chain, so it's not chain isomerism. You've got the same positions, 1, 2, 1, 2. So it's not positional isomerism. You've got the same functional groups, chloro, 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 so it's not functional group isomerism. This is something different. This is called geometric isomerism, and the specific example of geometric isomerism in Module 2 is where you have an alkene, okay, where the atoms are on different sides relative to the double bond. Here, they're both on the same side. Remember, the double bond can't twist. Okay? If this molecule here, if you drew it with the chlorine at the top, that whole end of the molecule can rotate round. The single bond can rotate. And so, if this atom was actually top left, those two would be the same molecule because it can rotate round. Whereas here, these two, they can't rotate. So there's no way that this molecule can be turned in space to turn into that molecule. And this is called geometric isomerism. Now you have to remember the labels E and Z. Okay, there are 2 ways to remember this. Firstly, if you think of a Z shape, then you think, well, it's going to be that one, isn't it? So you have to remember it's not. And that it's that one. The other way of remembering it, and this is perhaps even worse, is to go same side. Okay? Same side. Z means they're on the same side. You happy with that? And by same side, I don't mean there and there. If they were on the same side there and there, then you wouldn't have geometric isomerism. Okay? So they're on the same side, and that's Z, otherwise known as cis. Whereas this one here is trans, which means across, and that is E. Okay? So that is E, meaning across, or E meaning something in German, sorry, which is the same as trans, which is across, and that's Z. You happy with that? The last sort is optical isomerism, which we're not going to cover now, but is in Module 4, where you have two possibilities of 4 different groups around carbon, and those two are mirror images of each other. So, a few more details for you. Chain, different arrangements of the carbon skeleton, similar chemical properties, slightly different physical properties, and so on. Slightly different physical properties, more branching equals lower melting point. And that's because if you have more branching, the molecules can't line up as well. And if they can't line up as well, your van der Waals forces are weaker. Does that make sense? The van der Waals forces come from when the molecules line up and there's flickering dipoles between the two. Positional, same carbon skeleton, same functional group. Functional group is in a different position. Sometimes slightly different chemical properties. Okay, similar chemical properties, slightly different physical properties, usually again due to how well the molecules line up with their neighbours. Right, going back to functional group isomerism, here's where you have a different functional group but the same atoms, and here you have different chemical properties and different physical properties. A good example of this would be ethanol and here, dimethyl ether. I think that's the right name of the molecule. This one has got hydrogen bonding, okay, and is a relatively high melting point. This one hasn't, and its melting point has got much, much lower. Okay, so same atoms, different arrangement, different functional group, massively different chemical properties. Okay. Moving on then. I think that was 2, wasn't it? So, to just look at this in a bit more detail, here is my straight chain, here is my branch chain. Does it make sense that the butane straight chains can line up a bit better than these sort of T-shaped molecules here? Yeah? The better they line up, the stronger the van der Waals forces. Not a big difference, so the difference is between minus 0.5 degrees C is a boiling point, and minus 11.7 degrees C is a boiling point. So not a big difference, but still a difference. You should be aware that this is pent-1-ene and this is pent-2-ene, and that is again an example of positional group isomerism. Even though it's got double bond and you think it's going to be geometric, these two, positional group isomerism. Okay? Again, 1 chlorobutane, 2 chlorobutane, 3 is not 3 chlorobutane. Nearly fell into my own trap there. This is not 3 chlorobutane because you'd now number it from the right-hand side, so that becomes 2 chlorobutane again. And if you think about it, these two molecules are the same, but the other way around from each other. So if you were to rotate this molecule around in space, it would look like that. Does that make sense? And that's really the key difference. If a molecule can be rotated round in space to look like another molecule, they're not isomers. They're the same molecule. We're not going to worry too much about that. And that is the end of isomerism. Pause, please.